Okay, guys, I'm gonna start. So today's gonna be a little bit hard. The questions are really detailed, as I said in the email. And they're basically about the Krebs cycle, the glycolytic cycle, electron transport chain. So this is PS3, questions 6 and 7, the last two questions of our problem set. So problem number 6. Okay, so the question states the following yeast, real or imaginary, have mutations that alter the progression of glycolysis. For each case, predict the effect of the mutation in the context of energetic efficiency, ATP yield, redox balancing, and growth under aerobic or anaerobic conditions. Assume all yeasts utilize glucose as their primary sugar source. So this is kind of like the background information relating to the questions we're about to go over. So I'm going to move on. So 6A, a strain with a phosphofructokinase that only uses inorganic phosphate rather than ATP as a phosphate source and cannot bind ATP allosterically. So the answer to this is in bold. While this mutation will not stop the enzyme from forming the product, the Gibbs free energy of the reaction will significantly increase and likely become unfavorable, which, as we know, it's when the free energy is positive or greater than 0. This will reduce the energetic efficiency of glycolysis. The inability to bind ATP allosterically means PFK will continue to function unnecessarily during a high energy state. This may eventually lead to the halt of glycolysis, as energy will not exist in the system to catalyze the transfer of inorganic phosphate to fructose 6-phosphate. That probably is kind of like hard to understand, but I'll give you some time to look over. I'm going to go over in the next slide. I'm going to move on. So in terms of the content for this, so we have to look at the glycolytic cycle. So this is fructose 6-phosphate and phosphofructokinase, correct? So we have to know that the glycolytic reaction is favorable or spontaneous, which means the free energy here is going to be less than 0, or the free energy is going to be negative. That's why it's going to be spontaneous. And know that high level of ATP inhibits the enzyme phosphofructokinase, which is here, by decreasing its affinity for fructose 6-phosphate. So if ATP is not present, then phosphofructokinase will function unnecessarily at a high energy state where it's going to be non-spontaneous and change of G or free energy is going to be greater than 0. So does that make sense so far to everyone? Any questions? Okay. So no ATP means there will be no sufficient energy to help further the glycolytic reaction. So if we don't have energy, we can't move on, correct? It's going to be stuck here. So endergonic reaction means that the system will eventually run out of free energy to keep the glycolytic pathway going, and it's just going to add the inorganic phosphate to fructose 6-phosphate. So basically, since our reaction is not going to go forward, there's not going to be a spontaneous reaction, or change of free energy is not going to be less than 0, which is going to make it a positive, non-spontaneous reaction because it's going to be stuck here because we don't have ATP. So then the inorganic phosphate is just going to add on to the fructose 6-phosphate because we don't have ATP. Do you guys want me to explain that better? I know it's really confusing. Where did you get it? So I will move on if no one has questions. Okay, so 6B, a strain lacking the enzyme alcohol dehydrogenase. So alcohol dehydrogenase converts pyruvate to ethanol and simultaneously reoxidizes NADH. It is critical for glycolysis under anaerobic conditions. If alcohol dehydrogenase is lacking glycolysis under anaerobic conditions, we will not be able to occur, as NADH will not be able to be reoxidized. This means that ATP will not be produced rapidly when it is needed immediately. Okay. I'm going to move on and explain this a little more in depth. So the content is, there's acetaldehyde here, but we're just looking at the pyruvate going to the ethanol in our question. So dehydrogenase enzyme, just know that it catalyzes NAD plus and it yields to NADH. So the fermentation is what happens to pyruvate in the absence of oxygen or anaerobic conditions. So in anaerobic conditions, we can efficiently produce ATP by reoxidizing NADH to NAD plus. So when we regenerate NAD plus, we're able to reuse. So when we regenerate NAD plus, we're able to convert it back to NADH, and thus ATP can be produced also. And then like the glycolytic cycle can continue, or like happen again. And this is going to cause there to be two ATPs. Does that make sense? I feel like. Oh wait. So we see here, our alcohol dehydrogenase enzyme yields NADH, goes to NAD+, which helps our glycolytic cycle go, and then it's going to yield 2 ATPs, which is what we get from a glycolytic cycle. Do you guys want me to go back to the question and explain it, or is this content helping as I'm answering the question, like what I'm doing? You want me to go back? Oh, it's good? Okay. Okay, let me know, because it's really a lot of stuff is going on. Okay, so 6C, a strain that shortens glycolysis by catalyzing the following reaction: 1,3-bisphosphoglycerate plus ADP yields to 2-phosphoglycerate plus ATP. So what it means by shortening glycolysis, if you guys have memorized the glycolytic cycle, is that it skipped the 3-phosphoglycerate step. I'll show you. Here, let me just show you now. So it skips this step, 3-phosphoglycerate, and it goes from here to here. I'll come back to that. Okay, so the answer to this is question 6C. Originally, this conversion is catalyzed by phosphoglycerate kinase in combination with phosphoglycerate mutase. In this scenario, substrate level phosphorylation occurs and 2-phosphoglycerate is prepared without the need for phosphoglycerate mutase. Since phosphoglycerate mutase does not require energy or ATP, there is no change in energetic efficiency. So we can see here the bisphosphoglycerate goes here, and it uses a phosphoglyceromutase enzyme. And we can see that whenever you use a kinase enzyme, you have to like phosphorylate and use ATP. But if it's like, it's not kinase, for an example, if it's like mutase, then you don't have to use it. So because we're not using ATP here, it's not going to need any energy equivalence.
So aren't we making ATP at that stage?
Yes. Okay, so substrate level phosphorylation occurs in glycolysis, which occurs in the cytoplasm, and citric acid cycle, which occurs in the mitochondrial matrix. Oxidative level phosphorylation occurs in the electron transport chain, which is the inner mitochondrial membrane. And phosphorylation is ADP plus inorganic phosphate to ATP. Okay. I'm going to move on to the next slide. Okay, so 6D, a strain whose electron transport chain is unable to utilize oxygen to reoxidize the NADH produced by G3P dehydrogenase. So, if glycolysis was to continue via the aerobic pathway and NADH is unable to be reoxidized via the electron transport chain, NAD plus concentrations would significantly decrease until NAD plus becomes limiting. As a result, glycolysis would have to continue via alcohol fermentation, so NADH could be reoxidized. This would be short-lived, however, as the high alcohol concentrations may become toxic to the yeast. I'm going to move on, explain this better. So in aerobic conditions, NADH is unable to reoxidize because oxygen is not able to be utilized. So the only way we can reoxidize NADH is through alcohol fermentation, which is anaerobic. So you can see here we're not able to utilize oxygen, so that's why we're not able to reoxidize. So we have to use another method, which is through our anaerobic alcohol fermentation. So this just shows a reaction of G3P dehydrogenase. Go back to the question to see. So as you know, like I said before in part 6A, if we regenerate NAD+, we're going to be able to make ATP, correct, and further the glycolytic cycle. Okay, if no one wants me to explain anything else, I will move on. Okay, so question 6E, a strain with a deficiency in pyruvate kinase. So deficiency in pyruvate kinase will lead to increased levels of phosphoenolpyruvate, also known as PEP, and this is abbreviated as PK, pyruvate kinase, and decreased levels of ATP. This will not only decrease the energetic efficiency of glycolysis within the cell, but eventually lead to the stoppage of all cellular processes requiring ATP and cell death. So as I said before, kinase, whenever you see this enzyme, it usually has to do with phosphorylation, so ATP and ADP will be involved. So when pyruvate kinase is not there, there's not going to be any ATP able to generate. So because of that, we're going to run out of ATP, and eventually, like ATP, we need ATP for energy. So because of that, our cells will die, the ones requiring ATP, which is most of them. Okay. So content in regards to 6E is, remember that enzymes following a compound will inhibit that compound. For example, pyruvate kinase will inhibit phosphoenolpyruvate enolase, and enolase will inhibit 2-phosphoglycerate, and so on. So for example, we have here pyruvate kinase, right? So pyruvate kinase will inhibit this. Enolase will inhibit this. This will inhibit this. For example, hexokinase will inhibit glucose. And so if the pyruvate kinase is not there in phosphoenolpyruvate, it's going to increase in amount. So if we don't have pyruvate kinase to inhibit the phosphoenolpyruvate will keep functioning, and it's going to increase because there's nothing to inhibit it, no enzyme that's following it to inhibit. And also, I don't know if I went over the last point, but the inhibition of kinase that helps catalyze the reaction and produce ATP will cause a decrease in ATP because no kinase, no ATP, no phosphorylation. Okay. Anyone want me to explain anything better? I will move on. Okay, problem number 7, our last problem. So 7A, in humans, ethanol is metabolized by oxidation to acetaldehyde and then to acetate by the reaction shown in the diagram. So right here, why would metabolism of alcohol increase the amount of NADH, and what is the significance of this? So I don't know why I can't say this word. Metabolism of alcohol is first to acetaldehyde and then to acetate. So we can see here a reaction, acetaldehyde to acetate. So the formation of acetate from aldehyde is coupled with the reduction of NAD plus to NADH. So what this is saying is basically like, while this is happening, NADP plus to NADPH, this is happening at the same time. These essentially, although they're like different, like this is the pentose phosphate pathway, this is the like another one, this is what is it called, citric acid cycle. These are going to be the same reaction mechanisms, but they're different like pathways. But we're just going to use NAD plus to NADH so that it makes more sense to you guys. So this is as a reduction reaction that is required to balance the oxidation of aldehyde. This causes an imbalance in the cell of redox products, so NADH needs to be converted back to NAD+, thus favoring metabolism of pyruvate to lactate. So just a little hint here, lactate is anaerobic. So we need to regenerate NAD+. We can do that through anaerobic metabolism. I cannot say that word. But we need to regenerate that so we can create ATP and give off energy. And also alcohol has to do with anaerobic, as we know, so that's why it's going to increase, because we're using lactate. So it favors lactate as pyruvate to lactate is anaerobic and can regenerate NAD+ through reoxidation of NADH. So pyruvate also, I didn't put a diagram, but pyruvate has like, it can either go through the citric acid cycle, which is aerobic, but if it lacks then oxygen, then it's going to go through lactate, pyruvate to lactate, which is anaerobic, to regenerate NAD+, and that's how we get our energy, which is ATP. I'll move back to the last slide. I think I'm going pretty fast. We have one more left. Do you guys want me to explain anything? I'm going to move on to B, which is our last one. So in the production of wine vinegar, ethanol in wine is oxidized to acetate via acetaldehyde by aerobic bacteria from the genus Acetobacter. How does this bacteria recycle the NAD+ needed to form acetate? So as I said before, we're just going to do NAD plus NADH. And so NAD+, because it's coupled with this reaction, like it occurs at the same time as this. So NAD+ is recycled using the electron transport chain. The electron transport chain uses oxygen as a final electron acceptor, which is why this bacteria is aerobic. NADH is oxidized to NAD+ via the electron transport chain. This allows NAD+ to reform, which allows formation of acetyl-CoA, which enters into the Krebs cycle or citric acid cycle, the products of which produce ATP by both oxidative phosphorylation and substrate level phosphorylation. Now, if you remember, I said oxidative phosphorylation generates ATP through the electron transport chain, and substrate level phosphorylation has to do with the glycolytic pathway, generating ATP through that. Okay. So essentially, all these questions are kind of like different scenarios, but they're kind of the same. They all have to do with the regeneration of NAD+ to make ATP. Just different mechanisms for that. I'm going to move on to the last one. So this is electron transport chain here, which you guys should memorize for the test. So we have complex 1, complex 2 is here. Remember, complex 2 does not produce any protons. Complex 3, complex 4, and it ends here basically. And then this has to do with, this shows the previous problem of how the electron transport chain gets to convert, forms acetyl-CoA, which enters into the Krebs cycle. It kind of shows the mechanism of it. So we see our electron transport chain, and in complex 1, NAD plus goes to NADH. And so we're going to see the regeneration, and then you can see here, this is acetyl-CoA, it starts here, and it enters a citric acid cycle. Does that make sense a little? Just know how many protons are produced. This one, complex 2, does not produce any protons. Know how it goes from NADH to NAD plus, or NAD plus to NADH, succinate to fumarate. Last acceptor is an oxygen, electron acceptor is an oxygen acceptor, is oxygen, electron acceptor is oxygen. And then know about complex 3. Okay. Should I go back to the question before? Is everyone good? Okay. So I think that's it for today. But if you guys have any questions, let me know. I can move back to the slides. And this is our last workshop before the test. We won't have workshop next week, so don't come next week. And I think that's